For as long as humans have looked at the night sky, the moon has shown us only one face. Every culture, every generation, and every observer across thousands of years has seen the same familiar pattern, the same craters, the same dark Maria, the same face looking back at Earth. Yet the moon is not a static object. It rotates. It orbits. It moves through space like any other natural satellite. So why does its far side remain permanently hidden from Earth? The answer is a combination of orbital mechanics, tidal forces, and the long-term evolution of the Earth-Moon system. To understand why the moon behaves this way, we need to start with the relationship between rotation and orbit. Every rotating object has a rotation period, the time it takes to spin once on its axis. Every orbiting object also has an orbital period, the time it takes to circle around another body. For most moons in the solar system, these two periods are different. Jupiter's moons rotate independently. Saturn's moons show different faces as they spin. But our moon is different. Its rotation period and its orbital period are identical. It rotates once every time it orbits Earth once. This is known as synchronous rotation, or more commonly, tidal locking. Tidal locking is not a coincidence. It is a natural consequence of gravitational forces acting over very long periods of time. When the Earth and Moon formed, the Moon was not tidally locked. It rotated more quickly. But gravitational forces, the same type of forces that produce ocean tides on Earth, acted on the Moon's interior. In the earliest stages of the Earth-Moon interaction, the Moon was much closer to Earth than it is today. As a result, Earth's gravity exerted strong tidal forces on the Moon, deforming it slightly. This deformation produced a tidal bulge, a subtle stretching of the Moon's shape along the Earth-Moon line. This tidal bulge did not align perfectly with Earth. The Moon's rotation caused the bulge to shift ahead of Earth's gravitational pull. Because of this misalignment, Earth's gravity acted like a brake, creating a torque that gradually slowed the Moon's rotation. Over millions of years, this braking continued until the Moon's rotation slowed enough to match its orbital period. Once the two periods matched, the tidal bulge aligned perfectly with Earth and the torque disappeared. The Moon reached a stable configuration, the same hemisphere always facing Earth. This process is not unique to our Moon. It happens throughout the solar system. Mercury is partially locked to the Sun in a 3-to-2 resonance. Many of Jupiter's and Saturn's moons are fully tidally locked. Tidal locking is a common fate for any moon orbiting close to a large planet. In fact, most moons in the solar system present only one face to their parent planets. Our moon is simply the most familiar example. However, the moon's case is especially interesting because of how it reveals the history of the Earth-Moon system. When the moon first formed, likely from the debris of a massive collision between the early Earth and a Mars-sized planet, it orbited much closer than today, possibly just tens of thousands of kilometers away. At such a short distance, tidal forces were incredibly strong. These forces dissipated energy inside the moon, heating its interior and slowing its spin. Over time, as the rotational braking continued, the moon gradually receded from Earth. Even today, the moon is moving away from us at a measurable rate of about 3.8 centimeters per year. This movement is a direct consequence of the same tidal interactions that locked the moon in the first place. Synchronous rotation does not mean the moon shows exactly the same region at all times. Because the moon's orbit is slightly elliptical, and because its rotation is not perfectly uniform, we see a phenomenon called libration. Libration allows us to see slightly beyond the edge of the near side. Over the course of a month, observers on Earth can glimpse up to 59% of the moon's surface. But the remaining 41%, the far side, was first photographed in 1959 by the Soviet spacecraft Luna 3, revealing a dramatically different landscape dominated by craters and lacking the large Maria seen on the near side. The differences between the near and far sides are important clues to the moon's internal structure and geological history. The far side's heavily cratered surface suggests that its crust is thicker, possibly due to how the moon cooled after formation. The near side's thinner crust allowed large volcanic plains to form, creating the dark Maria that are visible from Earth. The far side, with its thicker crust, experienced far fewer lava floods. These structural differences may also be tied to the tidal locking process. The near side remained slightly warmer due to facing Earth and receiving more tidal heating, which could explain the asymmetry in crust thickness. Understanding tidal locking also helps explain why the moon's shape is slightly elongated rather than perfectly spherical. Over billions of years, the moon relaxed into a shape that aligns with Earth's gravitational pull. This slight elongation reinforces the locked orientation. If the moon were perfectly spherical, it would still likely lock, but the current elongated shape makes the lock more stable. If an external force, such as a massive asteroid impact, were to disrupt its orientation, the shape would naturally guide it back into alignment with Earth. The moon's orbital behavior also contributes to the stability of this locked configuration. Its orbit is not perfectly circular. It has an eccentricity that causes the moon to move slightly faster and slower at different points in its orbit. But because its rotational inertia and internal structure have settled into a stable state, the synchronous rotation persists despite these variations. The gravitational interaction ensures that any deviation from alignment produces a restoring torque that pulls the moon back into its locked orientation. On longer timescales, the Earth-Moon system is still evolving. As the moon continues to drift away, its orbital period increases. In response, Earth's rotation slows down. This is why Earth's days are gradually getting longer, a few milliseconds per century. In the distant future, Earth may become tidally locked to the moon as well, showing only one face to it. But this outcome is unlikely to occur before the sun evolves into a red giant and dramatically alters the dynamics of the solar system.
The long-term evolution of the Earth-Moon relationship also involves the transfer of angular momentum. When Earth was young, it rotated much faster. A day may have lasted only 5 or 6 hours. The moon's proximity caused strong tidal bulges in Earth's oceans. These bulges did not align perfectly with the Earth-Moon axis due to Earth's rotation. As a result, the ocean bulges pulled the moon forward in its orbit. This forward pull increased the moon's orbital energy and caused it to drift outward. At the same time, Earth's rotation slowed as rotational energy was transferred to the moon's orbit. This exchange of energy continues today. Earth's rotation slows by roughly 1.7 milliseconds per century. It is a small change, but over millions of years it accumulates significantly. Fossil records from ancient corals indicate that hundreds of millions of years ago, Earth had more than 400 days than a year, because each day was shorter. As the moon retreats farther into space, the gravitational link between Earth and the moon weakens. However, the tidal lock remains stable because the moon's rotation has already synchronized with its orbital period. Although gravitational locking dominates the moon's orientation, other external influences occasionally disturb it slightly. These disturbances include the gravitational pull of the sun, interactions with Earth's equatorial bulge, and the irregular distribution of mass inside the moon itself. These factors contribute to the small rocking motion that we call libration. Libration reveals slices of terrain just beyond the lunar edges, but the underlying synchronization remains intact. Understanding why the moon shows only one face also requires a look at the moon's internal structure. The moon is not a perfect solid. It consists of a crust, mantle, and core. These internal layers respond to tidal forces differently. Tidal locking is more efficient when a moon has a partially molten interior or a ductile layer that can deform and dissipate energy. Scientists believe that early in its history, the moon likely had a hotter and softer interior which allowed tidal forces to reshape it more easily. As the moon cooled and solidified, it settled into the synchronized state we observe today. The distribution of mass inside the moon also plays a crucial role. One major discovery from lunar missions is the presence of mass concentrations, or mascons, beneath the lunar surface. These are dense regions of rock buried under the lunar maria. Mascons affect the moon's gravitational field and influence its orbital stability. They also help keep the near side facing Earth by anchoring the moon in its locked orientation. If the mass distribution were completely uniform, the lock would still exist, but mascons make the stable configuration even more robust. The far-side terrain reveals more about the moon's history. Unlike the near side, which contains large, dark volcanic plains, the far side is dominated by highlands. The thicker crust on the far side likely prevented molten lava from breaking through the surface. One theory suggests that heat from the early Earth kept the near side warmer, thinning the crust and allowing volcanism to occur. The far side, being more insulated, cooled faster and developed a thicker crust. These differences were already present when tidal locking occurred and may even have contributed to it by increasing the asymmetry between the near and far sides. The fact that we see only one side of the moon has influenced human culture in profound ways. Myths, legends, and symbolism from every civilization have been shaped by the unchanging lunar face. The man in the moon, the rabbit on the moon, and many other cultural interpretations exist because the same features have been visible to every human observer for thousands of years. Without tidal locking, ancient cultures might have attributed different meanings to the lunar surface as it rotated freely, showing new patterns nightly. Scientifically, the locked configuration has significant implications for exploration. Because the far side never faces Earth, it is shielded from radio noise generated by human technology. This makes it an ideal location for radio astronomy. A radio telescope on the far side could observe cosmic signals without interference from Earth. Additionally, the far side provides unique geological insights because it has preserved features that the near side's volcanism erased. That is why several modern space missions focus on landing on or orbiting the far side of the moon. China's Chang'e 4 mission successfully landed on the far side in 2019, marking the first soft landing in that region. The mission revealed details of the far side surface composition and helped scientists understand differences between the two hemispheres. Future missions from NASA, ESA, and other agencies also plan to explore the far side more thoroughly. The far side's isolation and thick crust make it a natural laboratory for studying the moon's early history. Tidal locking also affects the moon's role in stabilizing Earth's climate. Because the moon is locked, its gravitational influence remains consistent. The moon's gravity plays a key role in maintaining Earth's axial tilt. Without the stabilizing effect of the moon, Earth's tilt could vary dramatically over long periods, possibly causing extreme climate variations. The relatively stable tilt we have today supports long-term climate patterns that allow life to flourish. In this sense, the moon's tidal lock indirectly contributes to Earth's habitability. However, the situation is not completely static. Over hundreds of millions of years, Earth's tilt still varies slightly due to gravitational interactions with other planets. But the presence of the moon keeps these variations within a range that is favorable for life. A world without a large moon might experience far more chaotic climate shifts. This is one reason scientists consider Earth's moon unusual among the terrestrial planets. Mars, for instance, has small moons and displays chaotic variations in axial tilt, which likely affects its climate stability. The Earth-Moon system is therefore a unique partnership shaped by gravity. Tidal locking is not merely a mechanical phenomenon. It is part of a long chain of interactions that link the histories of both worlds. When we observe the moon's unchanging face, we are witnessing the outcome of billions of years of gravitational evolution. The serene appearance we see from Earth hides a dynamic and complex history involving rotation, orbital mechanics, internal geology, and long-term energy transfer.
The unchanging view of the moon also influences how we explore it. Since only one side faces Earth, all early spacecraft, landers, and human missions targeted the near side. Communication is straightforward when the landing site is always in direct line of sight with Earth. By contrast, any mission to the far side requires relay satellites positioned in lunar orbit to maintain contact. This adds complexity, cost, and risk. For decades, this technical limitation prevented exploration of the far side entirely. But the far side's scientific value is immense. Shielded from Earth's radio emissions, it offers a pristine environment for studying faint signals from the early universe, signals that are nearly impossible to detect from Earth's noisy electromagnetic environment. Scientists envision placing large radio observatories in lunar craters on the far side to study cosmic dawn, the epoch when the first stars formed. Such observations could answer profound questions about how the universe evolved after the Big Bang. The far side's geology also provides clues to conditions during the moon's formation. Crustal thickness variations, the distribution of ancient impact basins, and the chemical signatures preserved in rocks all indicate that the near and far sides cooled differently. The far side's highlands contain some of the oldest surfaces in the entire solar system, largely unchanged for billions of years. Studying these regions helps scientists reconstruct the early history of planetary formation. The reasons behind tidal locking also have broader implications for exoplanet research. In many star systems, planets orbit so close to their stars that they are expected to be tidally locked, just like the moon. One hemisphere would experience perpetual daylight, while the other remains in eternal darkness. Understanding how tidal locking shapes climate, geology, and habitability on Earth's moon helps scientists model what life, if any, might be like on tidally locked exoplanets. These worlds may have narrow habitable zones near their terminator lines, where temperatures are moderate between the scorching day side and the frozen night side. Returning to the Earth-Moon system, tidal locking continually interacts with Earth's environment as well. The moon influences our tides, which shape coastal ecosystems and help regulate global ocean circulation. Tides disperse nutrients, affect marine life cycles, and contribute to the mixing of warm and cold waters in the oceans. Without the moon, Earth's tides would be far weaker and largely driven by the sun. This change would alter coastal environments in ways that could significantly affect the development of life. Another consequence of tidal locking is the predictable pattern of lunar phases. These phases, new moon, crescent, quarter, gibbous, and full moon, exist because the moon shows the same face while orbiting Earth. If the moon rotated independently, we would observe shifting surface features throughout the month. Instead, the steady, repeating phases have shaped calendars, agricultural cycles, and religious traditions across civilizations. From ancient Babylonian astronomy to modern timekeeping, the moon's locked rotation has influenced how humans measure time. The moon's stability also makes it an ideal destination for establishing long-term scientific bases. Future missions may construct observatories, laboratories, and habitats on both the near and far sides. The far side's radio silence makes it perfect for deep space communication hubs and telescopes, while the near side's visibility enables easier travel and supply routes. The locked orientation ensures that these advantages remain consistent. Although tidal locking appears permanent, the Earth-Moon system continues to change. As the Moon recedes farther, its orbital period increases. In distant epochs, the Moon will appear smaller in the sky and solar eclipses will look different. One day, the Moon will be too far away to produce total solar eclipses. Only annular eclipses will remain. Meanwhile, Earth's days will lengthen further. These gradual changes illustrate how the locked orientation is part of a dynamic and ongoing evolution. On geological timescales, tidal locking is extremely stable. But if we look far enough into the future, billions of years ahead, the situation could change dramatically. As the Sun expands into a red giant, its increased gravitational influence and mass loss will alter the orbits of planets and moons. The Earth-Moon system may be disturbed or even destroyed. But until that distant transformation occurs, the Moon will continue to show only one face to Earth. Understanding tidal locking is not just a lesson in orbital mechanics. It is a window into how gravity shapes celestial relationships. The same gravitational principles that lock the Moon also govern interactions between stars and planets across the universe. They explain why many exoplanets appear with one side scorched and the other frozen. They clarify the evolution of moons throughout the solar system. They reveal how gravitational energy is exchanged, transformed, and distributed over astronomical time. The Moon's locked orientation is a reminder that celestial objects are not isolated. They evolve together. The history of the Moon is inseparable from the history of Earth. Their tidal interactions have shaped the length of days, the stability of Earth's tilt, and even the conditions that made life possible. When we look at the Moon and see its familiar face, we are witnessing a record of billions of years of gravitational partnership. In summary, the Moon shows the same face to Earth because its rotation has synchronized with its orbit through a natural process driven by tidal forces. This tidal locking occurred early in the Moon's history when strong gravitational interactions slowed its spin. Over time, energy dissipation, internal deformation, mass distribution, and orbital evolution stabilized the configuration we see today. The result is a celestial relationship that has shaped not only the Moon's orientation, but also Earth's tides, axial stability, climate, and cultural history. The locked face of the Moon is more than a physical phenomenon. It is a symbol of the deep gravitational connection between two worlds. It is a reminder that the forces shaping planets and moons are subtle but powerful, unseen yet fundamental. And it is a testament to how the cosmos reaches equilibrium through interactions spanning billions of years. Don't forget to like, share, and subscribe to Wiseuse, where we uncover the science behind the universe one mystery at a time.